chapter 26. Current and resistance is what we'll be working on today. I'm Jake Zanny.
I'm Ramsey Habibi.
So
my dad's an engineer.
Okay, fine.
We're going to start chapter 26 off starting with current. That is I equals dq over dt, which is the change in the charge over the change in time. That comes out to coulombs per second, or the ampere. From there, we also go into current density, lowercase I. That equals the integral of J dot dA.
The capacitor is going to act as a wire initially. So the only way to really
This is scalar coordinates.
around that loop is worrying about resistor number 1.
dA here is a vector perpendicular to the surface area. The integral is taken over any surface, cutting areas over the conductor. Next, we're going to talk about junction rule. Basically, layman's terms, I in equals I out. So whatever current goes in through a point is the current that has to go out of the point. So if we look over here, we have 3 amps coming in from the left over here, and 2 amps coming out from the bottom. So you're going to get 5 amps exiting out of your system. Over here, we have a little bit of a trickier one. You have 1 amp going out this way, and 2 amps going out that way, which leads to a total of 3 amperes leaving somewhere in that direction away from this point. So then you have 5 amperes, because 2 plus 3, it's 5 amperes going that direction. You take that, and then you have 4 amperes also entering that direction. So you have a total of 9 amperes going that way. You have 3 going up that way, and 2 fighting against it. So you take 3 plus 2, and you subtract that from the 9, which gives you a total of 4 amperes coming out that way. Current and resistance are related, and you multiply them together to get voltage, or potential difference, as you'll learn later on in the chapter. This is measured in amperes, we already know that. Resistance is measured in ohms, and V is just measured in V. V stands for volts, although here it stands for potential. From there, you can rewrite the equation in a few different ways. You can have R equals V over I equals V over R. All say pretty much the same thing. It's just different ways to find different things out of the same equation. From there, we're going to go deeper into resistance. R equals rho, which is resistivity, L over A. So rho, or the resistivity, times the length over the area. Now we're just going to dip into the quick little correlation between resistivity and temperature. The correlation between these two are measured by P, rho minus rho initial equals rho initial alpha times T minus T initial. So the final resistivity minus the initial resistivity equals initial resistivity alpha times the difference between the final and the initial temperatures. First, we're going to look into Ohm's law. Ohm's law, in simplest terms, states that the current through a conductor between 2 points is directly proportional to the potential difference across the 2 points. That's just a fancy way of saying as V increases, I increases, or inversely, as V decreases, I will also decrease. Now we're going to look over here to the resistivity of a metal. This can be determined by the equation P, rho rather, equals mass of the metal over electrons squared n tau. Tau equals the mean time between the collisions of an electron with the atoms of the metal. Metals follow Ohm's law because tau is independent of E, which stands for the electric field, of any electric field applied to the particular metal. Now we're going to talk about power really quickly. Power equals current times the voltage difference or the potential difference. That particular equation is used when you're talking about electrical energy transfers. Power is measured in watts. Symbol for watt is just a W. From there, we also have resistive dissipation. God, that was a hard word to say. The equations for that are P equal to I squared R or V squared over R. Those are measured in joules per second, which are also the watts. Next, we have semiconductors and superconductors. Semiconductors have few conduction electrons, but can become conductors when doped with other atoms. Superconductors are conductors that lose all electrical resistance at a low temperature. All right, thank you for paying attention to me. Now I'm going to turn it over to my colleague, Mr. Ramzi Habibi.
Hi, I'm Ramzi Habibi, and I'll be doing some practice problems. If you open your book to page 700, and I'll do problem number 15. We have the conducting wire that's 1 millimeter in diameter, 2 meters in length, and 50 milliohms in resistance. So we have to find the resistivity, and Jake gave you a problem for resistance. We have R equals rho L over A. And then we can solve for rho. And now we know that the length is 2.
Are the drawings due today? Yes.
Yes.
But, you know, I didn't want your drawings one way or another.
And you can find the area using the diameter, and then you get 7.85 times 10 to the negative 7. And we know that the resistivity is going to be 0.05. So then when you solve for that, you get rho equals 2 times 10 to the negative 8 mega ohms. Alright, well, we're going to do problem number 37. We have a 3-volt battery. We have the energy is dissipated in the resistor at a rate of 0.54 watts. And we also have the power equation, which is P equals V squared over R. So now we just plug into the equation. We have the 3-volt battery, and the terminal is a 1.5 volt battery. So we do 1.5 over 3, square that, and then you multiply by 0.54. Then you get 0.135 watts.
Look at this. It's got that. Okay, that's creepy. If you think about it, that's creepy. Yeah! Alright. Roll. Doesn't even hurt. I'm not even hurt. You got stomach. You're dead. Oh no. Yeah! Look at the door. Cut your arm off.
Alright, thank you for paying attention to me. Now I'm going to turn it over to my colleague, Mr. Ramzi Habibi. Hopefully, Pompilli can spell his name this time and do his last name in the video. Pompilli, what's this symbol?